Multivariable Calculus 13.3, Day 2, and here's our second video of Day 2. We left off talking about the osculating plane, which of course was containing or was determined by the tangent vector and the normal vector, meaning that the binormal vector was perpendicular or orthogonal to it. But related to the osculating plane is an osculating circle. The circle that lies in that osculating plane of that curve at a point P is the same tangent as the curve is at P. It lies on the concave side of C toward which n points, and it has a radius of 1 over kappa, the reciprocal of the curvature. That's called the osculating circle. It's the circle that best describes how the curve behaves near that point. It shares the same tangent and normal and curvature at that point P. So let's jump on in and take a look at an example here where it says find the equations of the normal plane and the osculating plane of the curve in the previous example. First of all, a few reminders. As we're looking at this previous example, the curve in question that we saw was the cosine of t for our x component, sine of t for our y component, and t for our z component. And I guess what I really want us to take hold of is, yes, of course, we have a beginning point, x naught, y naught, z naught. But of course, we're also interested in a t value as well. And I guess what I want us to immediately take note of is that we're looking at t equals pi over 2. Get used to looking for little connections like that in the problem, where you'll be able to get a t value from the vector curve and the point in question, seeing what t could equal. But just a couple of reminders. You might remember that we had our unit tangent vector from the front page. We had 1 over root 2, and that's negative sine of t, cosine of t, comma 1. We had our normal vector, which was negative cosine of t, negative sine of t, and 0. And we also found our binormal vector. Whether you want to keep that 1 over root 2 inside or out is completely up to you. But we had those 3 basic vectors. So look, first off, we need to find the normal plane. To find the normal plane, that's the one that's determined, or it's going to contain, the normal vector and the binormal vector. And maybe this is the most critical aspect. The third vector in question, that is the unit tangent vector, is perpendicular to the normal plane. I'm going to give you a quick picture just to show what is happening. So we've got our plane right here. We can say, well, we've got our normal vector right over here. Perhaps we'll have a binormal vector over here. And then right up here would be our unit tangent vector. And that unit tangent vector, I guess what I really want you to see is this green vector that we're so used to seeing over here. It's like your ABC. So what we're going to do is more or less write the equation of a line of this plane here, but very, very, very critically, we're going to be plugging in a t value at pi over 2. And the reason why we're doing that, of course, is because that's when we're at the point 0, 1, pi over 2. So if we were to come back up here, we'd get 1 over root 2 negative sine of pi over 2, cosine of pi over 2, and 1. And of course that's going to be 1 over root 2. This is negative 1, 0, and a 1. And I guess what I really want us to take note of is we could use this exact vector right here, distributing that 1 over root 2 in. But just as well, guys, we could ignore that constant. You ignore the 1 over root 2, and gosh, does that bother kids sometimes the first time they're seeing it. Here's maybe the way to look at it. Look at this green vector right here. Regardless of how long it is, it's still going to be perpendicular. We could triple the length, we could multiply the length by pi or whatever. If we were not multiplying by 1 over root 2, we'd still have a perpendicular orthogonal vector. So here's what we also need to remember. Our x naught, y naught, z naught was 0, 1, pi over 2. So my word, all you have to do right now is to go back to what we had in chapter 12, and we work that out so very often. We're going to say right now we're going to have negative 1 for our a, and if you want to, we could even write this out real quickly just so that we remember where this is all coming from. Our a, b, and c, we've got all this written out here, and my goodness, it's just going to take a moment to write this tangent plane out. We've got negative 1, here's x minus 0, plus 0 times y minus 1, plus a 1 times z minus pi over 2, and set it equal to 0. And guys, you could leave it like this, or we could really just simplify this and write it in this way just as well. Here's the equation of a plane. In fact, it's the normal plane. So then they're asking for us to find the osculating plane. The osculating plane, well, here's the key. The binormal vector is the perpendicular vector. The osculating plane, like we said earlier, you've got a tangent vector, unit tangent vector right here. You've got your unit normal vector. That's what determines the osculating plane. But our binormal vector, that's the one that's perpendicular. That's the most critical part. That's knowing your A, B, and C. So, if we looked back up at the top right of the screen, we had this right here. We would like to plug in a t-value of pi over 2 once again. So that's going to be 1 over root 2. We've got the sine of pi over 2. We've got negative cosine of pi over 2. We've got a 1. And without too much work, I hope you can see that we'd have a 1, a 0, and a 1. So, that's your binormal vector at pi over 2. Well, of course, for our ABC, we don't have to have that 1 over root 2 there. We could just say it's 1, 0, 1, much like we did earlier. And we still have the same point, 0, 1 pi over 2. I think you can see that pretty quickly. So thankfully, what we'll have, just writing this out just like we did earlier, we can just plug in the appropriate values, and we'll have the equation of our plane. So we can do that right now. We can say our A is a 1. We'll have x minus 0. Our B, of course, is a 0. This is y minus 1. Our C is a 1, and we can have z minus pi over 2. By the way, even if you would have had the original binormal with that root 2's over it, you'd still get the same equation of the plane if you'd wind up canceling out that 1 over root 2 at the end. For the sake of time, I'm not even going to simplify this. This would be a valid equation of a plane. Obviously, we could simplify it quite a bit. It wouldn't be all that difficult. It would just be x plus z minus pi over 2 if you wanted to see that worked out. All right, well, our last part, we're going to find and graph the oscillating circle of y equals x squared. And y equals x squared, we all know, one of the most famous curves, one of the first algebraic curves that you've ever learned. Y equals x squared right here. We want it at the origin. We've got 0, 0. And we're trying to find and graph that oscillating circle. Here's something to help you, a little reminder. Kappa, you might remember from this chapter, had a wonderful, simple formula where it's not too much work. This is just going back to our basic function notation. We'd say kappa, the curvature, is going to be the absolute value of f double prime divided by 1 plus the first derivative squared, but taking that whole quantity, that sum, raised to the 3/2 power. Well, look, if we had f is equal to x squared, then f prime would be 2x, and f prime at 0 would be a 0. F double prime would just be a 2, and f double prime of 0 would still just be a 2. So if I'm going to plug in 0, 0, f double prime of 0 is just going to be the absolute value of a 2 up here. Down below we'll have a 1 plus. Well, first derivative plugging in a 0 is a 0. If we raise that up to the 3/2, doesn't take you too long to see that kappa equals 2. But please recall that a circle, including this oscillating circle, is always equal to the radius being 1 over kappa. Likewise, you could say kappa is 1 over the radius. Well, that means that r is going to equal 1/2. Well, I'll tell you what. We know that at 0, 0, there is a circle that really could be used to, approximate that curve close to that point of contact. The radius is 1/2, so from this point of tangency at contact, we'd move up here, we'd move up 1/2 steps away. So our center of the circle would be 0, 1/2, and of course our radius is 1/2. So what's the equation of a circle? Well, x minus h squared plus y minus k squared is equal to the radius squared, or I should make that lowercase. Well, you quickly would get x minus 0 squared plus y minus 1/2 squared is equal to 1/2 squared. And that's the equation of the oscillating circle. Obviously, you could simplify it just a little bit if you'd like. 1/2 squared is 1/4. You could see we've already graphed it, and that's what an oscillating circle looks like. It contains, obviously, the oscillating plane. And that wraps up 13.3.